Hi there, this is Truth Socrates. Welcome to video number 19 of my series for multivariable calculus, also known as Math 5C at Pasadena City College. So we've been doing triple integrals for a while now. We started out with a brick, and then we did a general solid last time. We did a tetrahedron, a solid tetrahedron. So we're going to continue with triple integrals because there's really a lot, so much to learn about triple integration. And today we're going to see a domain, a solid, where part of the boundary is not made with a plane figure. Okay, so a tetrahedron, as the name implies, is made of four sides, and each side is just a triangle, as we saw in the last video. So we're going to look at a solid today where a side or two, depending on how you count, I guess, is not made of something flat. Okay, so first thing we're going to do is review how to set up a triple integral in one of the three ways: type xy, xz, and yz. All right, so here's the type xy test. We're on page 134. You have to be like Superman. You have to be above the solid, facing down, and your right arm should be pointing towards the x-axis, your left arm pointing up towards the y-axis. Okay, so you will shoot arrows from below going up towards you. Okay, and those arrows should be entering the xy plane through a common footprint of the solid, and then entering the solid at a lower surface, z equals g1 of xy, and exiting at an upper surface, z equals g2 of xy. So here is the setup for a type xy integral. You integrate, do a double integral over our domain, and then a single inner integral from z equals g1 of xy up to z equals g2 of xy. Okay, you put your function inside, you have dz in your inner integral, and then your dA, which you can decide, will it be dx, dy, or dy, dx? Will you do a type 1 or a type 2? Okay, in the inner integral, we integrate with respect to z first. Think of x and y as constants. Once you get the antiderivative, you plug in the upper limit, plug in the lower limit for z, do the algebra, do the simplifications, then you subtract the two from each other. You are left with a double integral in the variables x and y. So you know what to do from there. So the other two kinds of solids, of course, have a similar construction. So here's a type YZ solid. You're facing the solid this time, standing on the xy plane, like a normal person, or like Wonder Woman. And there are arrows shooting towards you, parallel to the positive x-axis. So you're supposed to enter the YZ plane at a common projection of the solid onto the YZ plane. So there's your domain now. You will enter at a back surface, x equals g1 of yz, and then you will enter at a front surface, x equals g2 of yz. So here's the setup, and of course we're just basically permuting the symbols, the letters around. So you got the idea. The third kind of solid, though, is different from the other two, because this time you need to stand on the left side. In other words, the negative y-axis. Okay, that is important because you want to be looking towards the xz plane, where the x-axis, the positive x-axis, is to your right, the positive z-axis is going upwards. Okay, and this time the arrows are going away from you, so you are the one shooting the arrows from the left side. The arrows enter the xz plane at a domain, the common side view of the solid. The arrows enter at a left surface, a surface on the left, y equals g1 of xz, and they exit at a surface on the right of the solid, y equals g2 of xz. Okay, and of course here is the setup for that type of triple integral. Okay, so let's do a problem, and we get to do everything. We get to decide how to set it up and how to perform the integration. Okay, so here's the problem. We want to find the triple integral of 3y plus 4z over the solid E, which is the solid bounded below by the xy plane. So you have a floor, bounded above by another plane, z equals 5 minus 5/4 x. There's no y there, but that's okay. So it's slanting kind of this way. And bounded around by the cylinder, x equals y squared. Okay, so x equals y squared. There is no z term there. Okay, so yeah, how does this solid look like? So let's go to GeoGebra and sketch out. All right, so here we are, and I guess I need the xy plane. So let's put the, okay, so that's the floor, that's the bottom of our solid. And then we have the cylinder. So we have x equals y squared. I have the square over there. Ooh, there it is. Nice. X equals y squared. And we have plane. Z equals 5 minus 5/4 x. 5x over 4. Okay, so those are our surfaces. Can you see it? I hope your answer is no, not really. Okay, it's not very clear what the solid looks like, but maybe let's move it over here, and I guess we can make it scoot a little bit to the left, get over here. So there is our solid, okay? It kind of looks like a wedge, right? So you have this cylindrical surface. We cut it at the bottom at the xy plane, and we cut it above by this plane, z equals 5 minus 5x over 4. Okay, so yeah, I want to shoot arrows through this, and I want to see where the arrows enter, where the arrows exit. And this doesn't look like the diagrams that we've seen in the ebook so far. So next I want to show you how to draw this solid in a nice way. All right, so as a first step, let's take a look at it from the top. Okay, so we will see the parabola x equals y squared. Okay, just don't tilt too much or the surface will completely disappear like that. But it is cut off at x equals 4. Okay, so how did that happen? Okay, well, because we have this plane, z equals 5 minus 5x over 4, where do you enter the xy plane? When z equals 0. Okay, so if that whole thing is 0, move the 5x over 4 to the left, cancel the 5's, so you're going to get x equals 4. Aha, that is indeed x equals 4. So the bottom, the base of our figure, is a parabolic region. Okay, we have x equals y squared, and we end at x equals 4, and of course that's positive 2, that's negative 2. Okay, so the first thing we're going to do is let's go ahead and sketch that region. All right, so here's a fresh GeoGebra version, and so we can do a side-by-side comparison. Okay, so how are we going to do that base? All right, we are going to use surface, okay, which is now my favorite command. Okay, so how are we going to do this? All right, we want to draw that parabolic section. Okay, so y is going from negative 2 to positive 2, and x is going from x squared up to x equals 4. Okay, so here's what I do. I kind of put just dummy letters here for x, y, and z. And then I am going to put in two parameters. Okay? I usually use the letters u and v. Okay? U will go from -2 to +2. Okay? Who is the u here? X equals y squared, so u will be the y coordinate. Okay? And then v will go, for reasons that I will explain to you in a little bit, from 0 to 1. Okay, so we said that y coordinate is going to be the u. Okay, could I have used y over here instead? Yeah, but I personally, I don't want to use x, y, or z as a parameter. Just so I can distinguish it from the actual x, the actual y, the actual z. Maybe they're the same, maybe they're not, okay? But this is my habit, okay? My style. And you like it, great. You want to call that y instead of u. It's really up to you. You'll be programming with some of this. Okay, well, the plate is on the xy plane, so z is definitely a 0. Whoops, a 0. Okay, there you go. Okay, now what about the x coordinate? It's going to start at x squared, and it's going to end at x equals 4. Okay, so we want the x coordinate, it's going to start at y squared, and it's going to end at x equals 4. Okay, so this is where the concept of vectors can be useful and can be applied to the situation. Okay, so we want to start at y squared, so that's u squared. Okay, so u squared will be, oh, check it out. Okay, so that's the starting value. Okay, but I want to draw all the x coordinates from y squared up to 4. Okay, so right now I only have the x squared term. Okay, so how do vectors come in? Okay, the vector connecting x squared to 4, how do you do it? 4 minus x squared. Okay, so I'm going to put a plus sign here, and I will put 4 minus y squared, which is our u squared. Okay, close parenthesis. Okay, so we want that to, check it out. It showed up. Ooh, how did that happen? Okay, so if you want everything in between, you want the length of the vector to go from 0 to 1. That's where the v comes in. Remember, v in our parameter here is going from 0 to 1. Aha! So here's what we are going to do. We're going to put a v here, but GeoGebra is very sensitive. At this point, check how there's an exclamation point. It's like unknown command v, okay? Because to GeoGebra, this is a function, v of this, but we don't mean it as a function. We literally mean it as a product. So to make sure GeoGebra does not get confused, you put the times symbol. So asterisk, shift 8. Ooh, there it is. That is the base of our solid. Okay, it's on the xy plane, as you can see. Okay, excellent. So let's go back to our original attempt. Okay, this ugly thing. So now what are we going to do? Let's do the top. Okay, it's actually easier because it is right above that base. Ooh, okay, so maybe this is it a type? Oh, okay, so maybe you're starting to make a guess as to what kind of solid this is. Okay, so what are we going to do? Well, it will have the same x and y coordinate, but the z coordinate is no longer 0. Okay, what will the z coordinate be? Oh, there it is. 5 minus 5x over 4. Because we want to draw this portion of the plane. Okay, so who is the x again? Okay, it was that thing that we typed out. Okay, it was the longest part of that command. Okay, so all we have to do is copy that first command and then change the z coordinate. Okay, so next tab, here's what we can do. We are going to just say duplicate the input, please. Okay, so there it is. There are now 2 copies right there. But we don't want the z coordinate to be 0. Okay, we want it to be 5 minus 5x over 4. Okay, so 5 minus 5 parenthesis something over, whoops, no, down there, the 4. Okay, so all we do is copy this. Okay, so grab that, Control C, old school, Control V. Ooh, okay, so there it is. Isn't that beautiful? Okay, so that is now the top of our solid. Okay, so now we need the sides. Okay, at this point you might be happy with what we see already. Okay, and kind of just complete the solid in your mind, but why not? Okay, let's actually complete it with a third surface. Okay, so how do we do that now? Now I want to walk along the parabola, that is x equals y squared. And as I walk, I want to trace all the z values from 0 up to this plane, which is 5 minus 5y over 4, 5x over 4. Keep forgetting. Okay, so what is the command? Okay, let me scoot over here. So whenever I do the surface command, okay, once again, I just put dummy letters over there. And then I have a u and a v. Okay, so I want to walk around that parabola. So u will again go from -2 to +2. Okay, the v, as you might have noticed in the ebook, is always going from 0 to 1. I shouldn't say always, almost always going from 0 to 1. Because it's that vector that we want to go from 0 to the full length. Okay? Oh, but speaking of which, we start at the xy plane. So that's already 0. And we want to end up at this height. Okay? So unlike this, these two, where there's a u squared plus b times something, we don't need the bottom term, okay, because it's already a 0. Okay? So y is again our u. Our x is x equals y squared. So x equals u squared. Okay, so that will trace the curve, okay, the boundary, the parabolic boundary. Okay, so now the z. Okay, so v times, check it out. Okay, so right now v is going from 0 to 1. Okay, but we want it to end up at the plane, which has equation 5 minus 5 fourths x. Okay, so we will put that equation in. Feels familiar? 5 minus 5 fourths x. So 5 something over 4. Whoops, there it goes again. I don't know why. Okay, so we copy x. Oh, x is just u squared. Okay, so x is simple this time. So x equals u quantity squared. Ooh, there it is. Isn't that beautiful? Okay, so that is our actual solid compared to this ugly thing. Good. I don't even want to look at that anymore. Okay, you can't really do much with that solid, can you? Okay, this one, so much more satisfying. Okay, so where's our standard perspective? Right here. Okay, so here's the positive x-axis, positive y-axis, z. Okay, so this would be our front view. Okay, so when we're looking at that solid, we are looking at an upside down parabola. Ooh, so that is interesting. If we're looking at it from the top, okay, top view is over here. So remember, we have to be oriented correctly. Where is my x? There's my x. Okay, there's my y. That is the correct top view. Okay, very tempting to have the parabola going up. No, no, no. Positive x should be going right, positive y should be going up. That is the correct top view. It's still a parabola. Okay, remember that it is x, which is y squared. Okay, ending at x equals 4. Okay, what are we missing? The side view. Okay, so tilt it so that the z-axis is pointing up as usual. And we stand on the negative y-axis, which is where we are right now. And so we tilt it until we don't see the y-axis. And always a little tricky. There we go. Ooh, it's a triangle. Okay, that should make sense because we have this cylinder and we're cutting it with this plane, 5 minus 5x over 4. So we are getting a right triangle. Excellent. So now, how are we going to integrate this? Okay, so what was the function again? 3y plus 4z dd. 3y plus 4z. Okay, so let us go back to our solid. There it is. 3y plus 4z. I should write it down. 3y plus 4z. Okay, so maybe we don't want to integrate with respect to z right away. Maybe it would be better to integrate over the triangle. Yeah, maybe. Why not? Okay. Or to the upside down parabola. Okay, like this. Okay. So, yeah, I wonder which one is for the best. Okay, so it's actually possible to do it over all 3 kinds of domains. Okay, so let's start with the side. Okay, check it out over here. Okay, positive x on the right, positive z going up. Okay, so this is good because arrows going through the solid. Okay, and remember from the y for the xz test, the arrows are going away from you. Okay, so are you entering one surface? Yeah, you're entering over here. And are you exiting through another surface? Yeah, you're exiting over here on the other side. Okay, it is a symmetric solid with respect to the x-axis. Okay, except who is this? Who is this surface? Well, it came from the cylinder. It's a cylinder, right? So it is x equals y squared. So we need the y on the left and the y on the right. Okay, so you're going to need y equals square root of x, negative square root of, do we really want to integrate to have square root of x as a limit? I wouldn't recommend it, okay, because remember, you're going to plug this into your function, and who knows if you're going to get a square root of x, or you might be lucky and it will disappear and get squared maybe and become just x, okay? But that will depend on the function, okay? Oh, we have 3y. Yeah, we're gonna get, yeah, I don't want to go there. Okay, let's try something else, okay? Should we try the parabola here? This is the front view, okay? So, okay, we know what the footprint is. It's a parabolic plate as well. We need to find the equation of that parabola group. It came from y equals x squared, except that is definitely not y equals x squared, or even z equals x squared. Okay, that's the z-axis. This is the y-axis. Okay, so yeah, maybe that's not the way to go either. So I guess we are left with the top view. Okay, and should it be drawn as a type 1 or a type 2 double integral? Okay, so type 1 vertical. So again, you need a square root down here and a square root up here. Maybe not. Okay, However, if you go left to right, I'm sorry, left to right in this case is, yeah, you're looking this way. If you're going from -2 to +2 and you are shooting horizontal arrows, yeah, you're entering the parabola and you're exiting at um, x equals 4. Okay, so I do believe that that is our best. All right, so this will be our strategy. We will use the top view. We will create a type XY iterated integral. And the outer double integral, we scanned it as a parabolic base, as a type 2 region. Okay, so we will set up our integral. Y will go from -2 to +2. All right, so dy is on the outside. Let's put parentheses in there. And then x will be on the inside. Okay, so we'll have a dx there. X is going from, so the left edge is our parabola, x equals y squared, and the upper limit will be where the plate ends, which is at x equals 4. Okay, so that is our outer double integral. Okay, we still have the inner integral. Okay, so we have one more level, and that's now going to be dz. Okay, so edit, edit, edit. We will have z up here and z down here. Okay, so we still have to fill that in. Okay, oh, we do know the function, which is this 3y plus 4z. Okay, so we are missing the lower and the upper limits. Okay, so let's go back to our diagram. And okay, there it is. So where are we? Okay, it's a type XY solid. We need to shoot arrows from the bottom to the top. Okay, so we are Superman. We're flying up here with the x-axis to our right and our y-axis forward. Okay, so the arrows are going from low to high. They are approaching us. We're flying up here. They are all entering from the xy plane. Okay, that's good. That's z equals 0. They're all exiting at this plane. Ooh, we know who that is. That is z equals 5 minus 5x over 4. Okay, excellent. We have our balance. Okay, so at the lower limit, we have z equals 0. In the upper limit, we have 5 minus 5x over 4. The plane. Okay. All right, so there you go. That is our setup. That is the hardest part of doing a triple integral from scratch. Okay, many problems are like this. You want to find a triple integral over a domain. You know the function. It's usually pretty simple. I mean, that can only get simpler if you just had one term. Okay, but the domain is complicated. Okay, I mean, half of this time we were trying to sketch it out in GeoGebra. And then you still have a lot of work to do. You have to decide, are you going to do an XY, an XZ, or a YZ? Okay, which one will suit you best? Okay, so here we are. All right, so shall we start with the inner integral? Integrate with respect to dz. So integrate dz. And y is a constant, so we will get 3yz. 4z becomes 2z squared. Excellent. Okay, so we do have a square, but that's okay. You can actually factor out 5. Okay, that would be a smart thing to do. Okay, so at the upper limit, we will have 3yz. So we will replace z with 5 minus 5x over 4. And that's z with 5 minus 5x over 4. Forget the parentheses. There you go, quantity squared. So yeah, if you're If you want to do a little shortcut, yeah, how would we simplify this step by step? 15y minus 15xy over 4. Okay, take out the 5 and the other one, square it. 25 times 2, we're going to get 50. Okay, so 50 times, so the 5 is gone. 1 minus x over 4. Square, that's 1 minus x over 2 plus x squared over 16. I do believe 16. Okay, and then distribute that. Okay, so we know what to do. So will it? Oh yeah. Okay, there you go. Okay, so that distributed it for us. So what was my little shortcut, right? Whoops, doesn't do anything. Thank you very much. I have to do. Let me show you. There we go. I have to do compute and expand. Oh, there you go. 15y, correct, correct, and correct. So where did I go wrong? What? Okay. Oh, that's why. Stupid, so stupid. That should be x squared over 16. Let's try again. So compute and expand. Okay, now they're the same. Okay, things I have to go through. Okay, so that's just the upper. The lower, oh, thank goodness, it's a 0. Okay, so there are several advantages, I think, in doing it this way. Okay, so we know how to do the rest. Okay, it's now just a double integral. So so let's just write that down at z equals 0. Whoops, lowercase 0. There you go. Both terms go away. Both terms are 0. Okay, so we are left with a double integral. Okay, so let's copy it. Okay, so there's our triple. We have done the inner. Okay, so the inner integral, which is over here, we have computed. Okay, so I should remove this part, and we will put in this. Okay, so there it is. Okay, and you kind of know what to do from here. Okay, because that's now just a double integral. Are there some complications? Well, luckily, here's another advantage. Okay, even if we get an x squared or an x, yeah, we're gonna get xy, x squared, x cubed, and another x. So the worst is the x cubed. Okay, but the great thing is that even if you do a cube, okay, that's not terrible. Okay, you get y squared cubed, you'll get y to the 6. Okay, so what are the big steps? All right, so we have to find an antiderivative. Okay, so here's the fast way to do it in Maple. All I have to do is turn that into parentheses. Doesn't like square brackets. Okay, so who's the antiderivative? That is the antiderivative. Oh, factored out an x as well. Very interesting. Well, that's right, because all of the terms will get an x. Okay, and then you have to plug in x equals 4, put a 4 in there, x equals y squared, y squared, y squared, y cubed in all, y squared squared will be y to the 4, no y over there. There's another y squared. So you will get y to the 6 total. Okay, as our highest power, I should say. Okay, so you have to do the arithmetic, subtract all of that nasty stuff. And then, of course, finally, you will get the outer integral when everything is now just powers of y. Okay, so shall we just ask, oh great and intelligent Maple, what is the final answer that we are going to get? So remove the labels and turn the brackets into parentheses. Up and like this. Okay, so our final answer is going to be 2560 over 21. All right, very good. So that is our video for today. I hope you enjoyed it. Try out some of the problems. We are still going to stay with triple integrals for our next video because we are going to change the order of integration. So maybe you're getting flashbacks now from chapter 2, and I do hope that you were able to figure out those problems over there. So until then, I hope you enjoy the rest of your day. This is Socrates signing off. Thank you for watching. Bye.